Somewhere past the orbit of Neptune, a world roughly the size of Pluto is spinning so violently fast that it has been physically stretched into the shape of a rugby ball, completing a full rotation once every 9 hours, faster than any other known object, larger than 100 kilometers anywhere in the entire solar system. It's wrapped almost entirely in crystalline ice, bright enough to rival fresh snow. It carries 2 moons on strangely tilted, unstable orbits. And in 2017, astronomers discovered something nobody expected to find on a world this small, a ring, the kind of feature textbooks had spent decades insisting belonged exclusively to giant planets like Saturn and Jupiter. Its name is Haumea, and it might be the single strangest confirmed object in our entire solar system. To understand why Haumea exists in the shape it does, you first need to understand where it actually lives. Haumea orbits within the Kuiper Belt, a vast ring of icy debris extending beyond Neptune, similar in basic concept to the asteroid belt between Mars and Jupiter, but considerably larger, more distant, and populated almost entirely by frozen bodies rather than rock. Objects out here are called trans-Neptunian objects, and they're notoriously difficult to study, small, dim, and separated from Earth by distances that make even our most powerful telescopes struggle to resolve anything more than a single point of light. Haumea itself sits at an average distance of about 43 astronomical units from the Sun, far enough that sunlight, traveling at the fastest speed anything in the universe is permitted to move, still takes roughly 6 hours to complete the journey out to it. It takes Haumea about 285 Earth years to complete one full orbit of the Sun, following a genuinely eccentric path that, at its closest approach, actually brings it nearer to the Sun than Pluto ever gets, before swinging back out to considerably greater distances during the rest of its multi-century lap. Haumea's discovery, on its own, would be a solid story. The way it actually happened turned into one of the messiest, most contentious disputes in modern astronomy, a genuine scientific scandal playing out in real time across 2 continents. In late December of 2004, a team at Caltech, led by astronomer Mike Brown, working alongside David Rabinowitz and Chad Trujillo, the same trio already responsible for discovering the dwarf planet Sedna and soon to discover both Eris and Makemake, spotted an unusual object in images captured earlier that year at the Keck Observatory in Hawaii. Because they found it just days after Christmas, the team nicknamed it Santa amongst themselves, purely as an internal placeholder before any formal announcement. Independently, a separate team led by astronomer José Luis Ortiz Moreno at the Sierra Nevada Observatory in Spain had also been quietly searching the same region of sky, and in July of 2005, while reviewing older archival images taken back in March of 2003, Ortiz's team identified the same object in their own data. On the 27th of July 2005, the Spanish team emailed the International Astronomical Union's Minor Planet Center, formally claiming the discovery, just 1 week after Brown's team had published an online abstract previewing their own upcoming announcement at a conference. What followed wasn't a polite academic disagreement. Brown publicly accused the Spanish team of quietly accessing Caltech's own telescope observation logs, which were, at the time, technically viewable online, and using that information to specifically go looking for the object in their older archival images, right before rushing out their own competing claim. Ortiz and his team denied any wrongdoing, and in turn accused Brown's team of exerting political pressure on the IAU to favor the American claim. The dispute dragged on for years, and the International Astronomical Union ultimately took an unusual middle path. Rather than officially crediting either team as the sole discoverer, a decision it has never fully clarified, the IAU listed the discovery location as Spain's Sierra Nevada Observatory, formally acknowledging the Ortiz team's priority and submission. While still accepting the name Haumea, the option originally proposed by Brown's Caltech team, honoring the Hawaiian goddess of childbirth and fertility over the Spanish team's preferred name, Atasina, an ancient Iberian goddess of spring, which the IAU rejected on the technical grounds that naming conventions for this category of object required a creation deity specifically. It remains, to this day, the only dwarf planet in the solar system without a clearly officially credited discoverer, a genuinely unusual asterisk hanging over one of the more important astronomical finds of the early 2000s. Getting even basic physical measurements out of an object this small and distant required its own kind of scientific ingenuity, since Haumea, unlike Pluto, has never been visited or directly imaged in any detail by a spacecraft. Astronomers instead lean heavily on Haumea's own moons to determine its mass, applying a version of Kepler's third law, the same basic mathematical relationship that describes how planets orbit the Sun, adapted here to describe how Hi'iaka and Namaka orbit Haumea itself. By precisely measuring each moon's orbital period and distance from Haumea, researchers can work backward to calculate the mass Haumea's gravity must have in order to hold those moons in exactly the orbits observed, a technique that's proven remarkably reliable across the solar system, since it's the exact same underlying method astronomers used to weigh Pluto once its own moon, Charon, was discovered in 1978. That calculation places Haumea's mass at roughly 1/3 that of Pluto, making it one of the more massive confirmed dwarf planets, despite its unusual, elongated shape, meaning its longest dimension actually exceeds Pluto's own diameter, even though the two bodies are frequently described as being roughly comparable in overall size. Even after the naming dispute settled, Haumea kept producing surprises, starting with something as basic as its actual shape. Every other confirmed dwarf planet in the solar system, Pluto, Eris, Makemake, Ceres, is roughly spherical, or close enough to spherical that the difference barely registers to the eye. Haumea isn't. Careful measurements place its longest axis at roughly 2,320 kilometers, its intermediate axis at around 1,700 kilometers, and its shortest axis at only about 1,140 kilometers, numbers that describe something closer to an American football or a slightly squashed rugby ball than a planet. That elongation isn't a measurement error or an optical illusion caused by Haumea's tumbling orientation as astronomers observe it. It's a genuine physical consequence of exactly how fast the object spins. To understand why spin alone can distort a solid icy world into that shape, it helps to think about what happens to any rotating body as its rotation speeds up. Spin something fast enough, and centrifugal force, the same effect that presses you sideways into your seat on a tight turn, starts pulling material outward along the equator while the poles remain comparatively unaffected. Spin a planet slowly, like Earth, and that effect produces only a very slight equatorial bulge, barely noticeable without precise measurement. Spin something as fast as Haumea does, completing a full rotation once every 9 hours compared to Earth's 24, and that same effect becomes dramatic enough to physically reshape the entire object into an elongated ellipsoid. Haumea's rotation is so extreme that researchers studying it have concluded it sits almost exactly at the theoretical maximum spin rate a body of its size and composition could sustain without being torn apart entirely. Speed it up even slightly further, and rather than simply stretching more, the object would likely become unstable and begin shedding material or splitting apart outright. This raises a genuinely reasonable question for anyone who's followed the broader story of dwarf planet classification since Pluto's 2006 demotion, because one of the specific criteria the International Astronomical Union uses to define a dwarf planet is that the object must have enough mass, and therefore enough of its own gravity, to have pulled itself into what's called hydrostatic equilibrium, a state where the object's shape is governed by the balance between gravity pulling inward and internal pressure pushing back outward, typically producing something close to a sphere. Haumea, quite obviously, isn't spherical at all. So how does it still qualify? The answer lies in a detail that's easy to miss in a casual explanation of hydrostatic equilibrium, which is that the concept doesn't strictly require a sphere. It requires a shape determined by the balance of gravity, internal pressure, and, in the case of a rotating body, the centrifugal forces generated by that rotation. For a slowly rotating object, that balance does produce something very close to a perfect sphere. But for a rapidly rotating body like Haumea, the same underlying physics can instead produce a stable, elongated shape called a Jacobi ellipsoid, a genuine, well-understood solution in the physics of rotating fluids and self-gravitating bodies, first worked out mathematically in the 19th century by mathematician Carl Gustav Jacob Jacobi, long before anyone had ever observed a real astronomical object shaped that way. Haumea's elongated football shape isn't a violation of hydrostatic equilibrium. It's a textbook example of what hydrostatic equilibrium actually looks like once you introduce sufficiently fast rotation into the equation, making Haumea, as far as astronomers currently know, the only confirmed body in the solar system holding this specific kind of stable, rotation-distorted shape. That leaves an obvious follow-up question. Why is Haumea spinning this fast in the first place? Nothing about a typical trans-Neptunian object's formation history should naturally produce rotation this extreme, and the leading explanation researchers have converged on ties directly into the next genuinely strange piece of Haumea's story, its moons. For roughly 20 years after Haumea's underlying object was first noted in old survey images, nobody suspected it had any moons at all. That changed on the 26th of January, 2005, when astronomers using the W.M. Keck Observatory in Hawaii detected a small satellite orbiting the object, discovered right around the same period Brown's team had been internally nicknaming the parent body Santa, which led them to give the newly found moon the temporary nickname Rudolph, after Santa's most famous reindeer. That name didn't survive the formal naming process. The moon was eventually renamed Hiaka after a Hawaiian goddess associated with the island of Hawaii itself, fitting naturally alongside the parent body's own Hawaiian name. Hiaka turned out to be the larger and brighter of Haumea's two known moons, measuring roughly 320 kilometers across, orbiting on a nearly circular path at a distance of about 50,000 kilometers, completing one full orbit every 49 days. Spectroscopic analysis of the light reflecting off its surface revealed something telling, an infrared signature dominated by nearly pure crystalline water ice, very similar to the surface composition of Haumea itself. A second, smaller moon turned up later that same year, spotted on the 30th of June, 2005, and given the equally festive temporary nickname Blitzen, another of Santa's reindeer, before eventually receiving its own permanent name, Namaka, after a Hawaiian water spirit associated with tides in the sea. Namaka is considerably smaller than Hiaka and orbits much closer to Haumea, completing a full lap in roughly 18 days on an orbit that's noticeably more elliptical or stretched than Hiaka's nearly circular path. Observations made in 2008 revealed something genuinely puzzling about how Namaka's orbit is oriented, tilted by roughly 133 degrees relative to Hiaka's own orbital plane, a substantial persistent misalignment that shouldn't, under normal circumstances, still exist. Over long enough timescales, the gravitational tug between orbiting bodies, tidal forces, generally works to smooth out exactly this kind of orbital eccentricity and tilt, gradually pulling orbits into flatter, more circular, mutually aligned paths. The fact that Namaka's orbit remains this eccentric and this steeply tilted suggests either that the system is younger than it might otherwise appear, that some other gravitational disturbance has kept perturbing it, or both, and researchers studying the system haven't yet fully settled on which explanation, or combination of explanations, is correct. The composition of both moons offers the biggest clue toward explaining Haumea's extreme spin, because the infrared spectrum of Hiaka closely matches Haumea's own surface, both dominated by nearly pure crystalline water ice, an unusual enough surface composition on its own that it strongly implies a shared origin rather than a coincidence. The leading theory, championed prominently by Mike Brown himself, proposes that a massive impact, sometime in Haumea's distant past, struck the object with enough force to blast a significant portion of its icy outer shell off into surrounding space, while simultaneously spinning up the remaining body to the extreme rotation rate we observe today, in much the same way a figure skater spins faster by pulling their arms inward, except here the mechanism runs in reverse, an impact redistributing angular momentum in a way that dramatically accelerated the surviving object's spin. The debris blasted free by that same impact, according to this model, later reassembled under its own gravity into the moons Hiaka and Namaka, explaining why both share such a similar icy composition to their parent body. A competing, more elaborate version of this idea proposes an even messier history, that the initial collision's debris first coalesced into a single larger moon, which was later struck again in a second separate impact, shattering that moon and scattering its fragments back outward, eventually producing the two moons and additional debris astronomers observe today, essentially a collision on top of a collision. Testing which version, if either, is correct runs into a genuine statistical problem, though, because the Kuiper belt as it exists today simply isn't dense enough for a collision this significant to be a common expected occurrence. Researchers have calculated that the odds of two objects of the necessary size actually colliding within the Kuiper belt's current population are below roughly 0. 11% over the age of the solar system, a genuinely low probability for an event this important having actually happened. That statistical problem has pushed the leading hypothesis in a different direction entirely, that Haumea's formative collision likely didn't happen in the Kuiper belt at all, but rather in a a considerably more crowded region closer to Neptune's original orbit, sometime before Neptune's own outward migration during the early solar system's turbulent history, scattered that region's population thin, flinging Haumea and its collisional siblings outward into the comparatively sparse Kuiper Belt region we find them in today. That collisional origin story connects directly to one final, genuinely remarkable discovery, which is that Haumea isn't alone out there in any sense beyond simply having two moons. It has an entire extended family. Astronomers have identified a cluster of other trans-Neptunian objects sharing strikingly similar orbital characteristics, and critically, a similarly unusual icy surface composition dominated by crystalline water ice, a spectral signature rare enough elsewhere in the Kuiper Belt that finding it repeated across a whole group of related bodies is considered strong, direct evidence they all share a common origin. This grouping, informally called the Haumea family, represents the first confirmed collisional family ever identified among trans-Neptunian objects, a scattered population of siblings, all apparently blasted free from the same parent body during whatever violent event originally spun Haumea up to its current extreme rotation rate, as if an egg-shaped, hyper-spinning dwarf planet with a family of collisional siblings and two oddly misaligned moons wasn't enough. Haumea delivered one more genuine surprise in 2017, using a technique astronomers had relied on for decades to study distant solar system objects, indirectly stellar occultation. The method works conceptually like a very precise, very distant eclipse. When a foreground object, in this case Haumea, passes directly between Earth and a background star, from our specific vantage point, that star briefly dims or disappears entirely as Haumea's body blocks its light, and precisely timing exactly when and for how long that dimming occurs, observed simultaneously from multiple locations spread across Earth's surface, lets astronomers reconstruct an object's true size and shape with far more precision than direct telescope imaging alone could ever achieve for something this small and distant. In January of 2017, an international team, including a substantial contingent of Brazilian researchers, and led once again by José Luis Ortiz, the same astronomer who had shared credit for Haumea's original discovery, organized a coordinated observation campaign to catch exactly this kind of occultation, specifically hoping to nail down Haumea's precise dimensions. What they found, in addition to the expected size measurement, was a second, smaller, unexpected dip in the star's brightness occurring shortly before and after the main occultation event, a pattern that made sense only if something else, something considerably fainter and thinner than Haumea itself, was also partially blocking the star's light on its way past. Follow-up analysis confirmed it, a genuine ring system encircling Haumea's equator, the first ring ever confirmed around any object in the Kuiper Belt, and only the second ring system ever found around a body that isn't one of the 4 traditional giant planets, following the discovery of rings around the much closer Centaur object Chariklo just a few years earlier in 2013. Chariklo, a much smaller icy body orbiting between Saturn and Uranus, rather than out in the Kuiper Belt, had already forced planetary scientists to accept that ring systems weren't strictly a giant planet phenomenon, but Haumea's ring pushed that revised understanding even further out into the solar system and around an object considerably larger and more complex than Chariklo, itself only about 250 kilometers across. Haumea's ring measures roughly 70 kilometers wide, forming a complete circle with a diameter of approximately 2,300 kilometers, and it orbits in a genuinely striking 3-to-1 resonance with Haumea's own rotation, meaning every individual ring particle completes exactly one full orbit around Haumea for every 3 times the dwarf planet itself spins on its axis, a precise, mathematically locked relationship that strongly suggests the ring's structure has been actively shaped and maintained by Haumea's own gravity, rather than existing as loose, randomly distributed debris. Composition-wise, the ring is thought to be built from broadly similar material to Saturn's much larger, much more famous rings, a mixture of ice and rock fragments ranging from grains barely bigger than sand up to chunks several meters across. Before this discovery, ring systems were treated in most textbooks as a phenomenon essentially exclusive to giant planets, explained by the sheer scale of their gravity and the abundance of orbiting debris in their immediate surroundings during the early solar system. Haumea's ring, along with Chariklo's smaller one, forced a genuine, meaningful revision to that assumption, demonstrating that a comparatively small, icy world, far smaller than any of the gas giants, can still capture and maintain a stable ring system under the right conditions, opening a real, still actively investigated question about how many other small, distant Kuiper belt objects might be quietly hiding rings of their own, waiting for the right occultation and the right timing to finally reveal them. Haumea's surface itself adds one more layer of genuine puzzle to the story. Telescopic measurements indicate the dwarf planet reflects an extraordinarily high percentage of the sunlight that reaches it, comparable to fresh, undisturbed snow, a property astronomers call high albedo. Roughly 80% of Haumea's surface appears to be covered in nearly pure crystalline water ice, and crystalline ice specifically, rather than the more common amorphous form, is itself a meaningful clue, since forming and maintaining crystalline ice generally requires some source of relatively recent warming, whether from an ancient impact heating the surface layers, some form of ongoing internal heat leaking outward from Haumea's interior, or a combination of both. Left completely undisturbed at Haumea's extreme distance and correspondingly frigid surface temperature, water ice would be expected to gradually revert to its more disordered, amorphous form over time under constant low-level bombardment from cosmic radiation, which makes the crystalline ice actually observed on Haumea's surface a small, ongoing scientific puzzle in its own right, hinting at a surface that's been reshaped, reheated, or refreshed more recently than a purely quiet, undisturbed history would predict. Spectroscopic data has also picked up traces of other materials mixed into that ice, potentially including hydrogen cyanide compounds or clay-like minerals, along with inorganic cyanide salts, additional evidence pointing toward a more chemically and geologically active history than Haumea's small size and extreme distance from the Sun would otherwise suggest. It's genuinely worth pausing on how much of this story rests on indirect inference rather than direct observation, because unlike Pluto, which received an extraordinarily detailed, close-range visit from NASA's New Horizons spacecraft in July of 2015, no mission has ever been sent to Haumea, and none is currently funded or scheduled to change that. Every image the public has ever seen of Haumea, the elongated, icy, ring-encircled world depicted in documentaries and articles, is an artist's interpretation, built from the genuine, carefully gathered data astronomers have painstakingly assembled, its rotation rate, its axis measurements, its surface composition, its rings' exact dimensions, but never confirmed by an actual photograph taken up close. Through even the most powerful telescopes currently available to astronomers, Haumea still appears as nothing more than a single faint point of light, occasionally flickering in brightness as its elongated shape rotates into and out of view, orbited by two even fainter points representing its moons. Every genuinely strange detail covered in this video, the extreme spin, the football shape, the ring, the misaligned moons, the crystalline ice, was extracted entirely from patient, indirect measurement, brightness curves, spectroscopic analysis, and a single, carefully coordinated stellar occultation observed from the ground, rather than from a single clear photograph. There have been early conceptual discussions among planetary scientists about what a dedicated mission to Haumea might eventually look like, following the same broad model NASA used for New Horizons, a relatively lightweight, fast flyby probe rather than a full orbiter, given how forbiddingly long any round-trip communication or full orbital insertion at that distance would take. No such mission currently has funding, a formal design, or a launch date, and given the roughly decade-long transit time similar missions to the outer solar system have required, along with the years of planning that typically precede launch, a realistic flyby of Haumea likely remains multiple decades away, even in an optimistic scenario. Until then, everything scientists learn about this world will continue to come the same way it has since 2004, through patient, indirect observation from Earth and Earth-orbiting telescopes, piecing together an increasingly detailed picture of an object nobody has ever actually seen up close. That's arguably what makes Haumea's story so worth sitting with in the end. It's not a world humanity has ever actually seen up close, and given current mission budgets and priorities, it likely won't be for a very long time, possibly not within the working lifetime of anyone reading this. And yet, through nothing more than careful, patient observation from roughly 4 billion miles away, astronomers have managed to reconstruct an object shaped like a spinning rugby ball, encircled by a precisely resonant ring, trailed by two moons, with a genuinely puzzling orbital history, and surrounded by an entire family of icy siblings scattered across the outer solar system by a violent collision that likely happened billions of years ago, in a completely different region of space than where Haumea sits today. It's a genuine testament to how much modern astronomy can extract from starlight alone, and a reminder that some of the strangest, most genuinely alien places in our own solar system are still sitting out there, essentially unphotographed, waiting for the technology, the funding, or simply the scientific priority to finally point a spacecraft their way. If stories like this pull you in, subscribe to the channel, because this is exactly the kind of territory we spend our time exploring here. Drop a comment and tell me which part surprised you most, the messy, still unresolved dispute over who actually gets credit for discovering Haumea, the fact that its extreme spin is what legally allows it to qualify as a dwarf planet despite not being round, or the idea that an object this small and this far away somehow holds onto its own ring system. Let me know where in the world you're watching this from, and if you want to keep exploring, there's another documentary waiting for you right here on the channel, so stay a little longer, and let's keep looking out toward the edge of everything we've mapped so far.